Hello and welcome back to my channel. So today we're going to be talking about the Lagrange Error Bound. So Lagrange Error Bound and Taylor polynomials are two things that kind of go together. Let f be a function that has n plus 1 derivatives in an interval containing c and x. C is our center like before, and x is going to be just any number that we want. Generally rational or irrational. It just needs to be some number that we can plug in for x. There exists a value z between x and c such that two things are true. The first thing being our function f of x is equal to Pn of x plus Rn of x. So Pn of x is what we talked about last time with Taylor polynomials. So this is a Taylor polynomial. The second piece here is our error, the remainder of what we have left over. The polynomial that we make, the Taylor polynomial, is not going to be an exact match to our function because we end at a certain n value, but it becomes really close. So this equation over here is going to be that remainder, the parts that we are missing. Okay, so this is our function. The other caveat here is we have a formula for this remainder. So where r sub n of x is equal to a very specific function. That function is the n plus 1 derivative of f evaluated at z divided by n plus 1 factorial times x minus c to the n plus 1. Okay, so this might look similar to the alternating series error bound where we're looking at the next term. So if we are looking at what we have here, this is very similar to finding the next term of a Taylor polynomial. The big difference is this value z that we don't necessarily know, and we don't know what it's going to be. So we can kind of think about it as the next term, which is how we might remember this equation. Okay, so the Lagrange error bound. So the Lagrange error bound says that we may not be able to find that exact remainder, but we can get a good idea of it. And what it says is the absolute value of our remainder function is less than or equal to the absolute value of x minus c to the power of n plus 1 divided by n plus 1 factorial. All of this is that remainder function except for that n plus 1 derivative of f evaluated at z. And what we're going to do with that, because we also need it, is we're going to multiply this by the maximum of, so the absolute max of the n plus 1 derivative of f evaluated at z. So the big piece here that we don't know how to find yet is going to be this maximum. And that's what we're going to be figuring out to do. So all of this comes from the fact that the absolute value of our remainder is equal to, so the absolute value of r sub n, that remainder function, is equal to the absolute value of our function minus our Taylor polynomial. So here are some things that we kind of need to know. So the first thing that we need to know is that we are not finding what the actual error is. We're not finding this actual error. So we will not be finding r sub n. we are going to be finding what bounds it. So we're going to be finding the thing that it could be, the biggest it could be, or the smallest it can be. The next thing is we are using the first unused term to find that error. So just like the alternating series test, in order to find that error, we're going to use that n plus 1 term. So we're using this n plus 1 piece. We often overestimate the error bound since we rarely can find the actual value of this max. So we're going to be probably overestimating, but we also need to be able to figure out how to accurately overestimate. And we won't be finding the actual maximum. So we will find the value of this maximum generally by looking at a graph. So looking at a graph of that derivative. If f of x is sine or cosine. So in sine or cosine, sine and cosine oscillate between two values. Those values being positive 1 and negative 1. The maximum between those two is positive 1, so the highest it will ever be is positive 1. So when we see sine or cosine, we already can kind of find that maximum for us. And the third way that we find this maximum is we are told directly in the problem what is happening. So these are our three options. They will give us a graph, they will give us sine or cosine, or we are going to be told in the problem directly or indirectly, which means we have to figure it out from there. Okay. So let f be a function with 6 derivatives on the interval of 1 to 1.4. It is known that the sixth derivative f of x is less than or equal to 0.7 for all x on the interval of 1 to 1.4. If a fifth degree Taylor polynomial is used, Taylor polynomial for f is centered at x equals 1 is used to estimate f of 1.4. Calculate the Lagrange error bound to determine the accuracy of this approximation. So we want to use the Lagrange error bound. So the Lagrange error bound is that r sub n, or the absolute value of r sub n of x is less than or equal to that next term. So the absolute value of x minus c to the n plus 1 divided by n plus 1 factorial times this maximum. Okay, so based off of the problem, we need to know what c is, we need to know what n is, we need to know what x is, and we need to know what the max is. So the first thing I can see is centered at x equals 1, so I know our center is 1. We have a fifth degree Taylor polynomial, so n is 5. We want to approximate 1.4, so 1.4 is our x value. The other thing it is that f to the n plus 1, so we are looking at f to the 5 plus 1, which is 6 of z. So we want the max of this. Well, the problem told us the sixth derivative is less than 0.7 for all values between 1 and 1.4. So that means the max that we're going to use is 0.7. We're not going to change it to something else. We're going to leave it as 0.7, and it is okay that we are overestimating on this because that is what it gave us. So what we're going to do now is plug in what we know. So r sub 5 of 1.4. So we know n is 5, x is 1.4, is less than or equal to the absolute value of x, which is 1.4, minus 1 to the 5 plus 1 divided by 5 plus 1 factorial. And then we know the max, so this whole thing goes to 0.7. And then we're going to simplify. So the absolute value of r sub 5 of 1.4 is less than or equal to the rest of this, so we have 0.4 to the 6th power divided by 6 factorial times 0.7. This is something that we're going to use a calculator for because error bounds like this are going to be really, 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 really small. So they expect us to use a calculator on this. If we use a calculator on this, we get that the absolute value of r sub 5 of 1.4 is going to be less than or equal to the following decimal, 0.0000398. So kind of our two options, they may give us something that looks like this as an answer, or they're going to expect a decimal, which means you're going to be using a calculator. So that is all it's going to be when we look at a problem that's given to us and all the information is given